This short video is a quick introduction to the Python population modeler to explain how we can use it to study and characterize the COVID-19 epidemic. So if you go to the website www.pyPM.ca, you'll get to this point where you can read more information, but I'll quickly just go through some of the features of this population modeler. So one of the first things you'll see is that there is a graphical user interface available, and there's a quick way to get started. Just to take a look at pyPM by clicking on that link. That'll take you to a page that has different options. You can either start with Binder or with a Jupyter Hub. So in Canada, we have a network of Jupyter Hubs at various institutions. And just by clicking on an institution that you might have a association with, you can use that Jupyter Hub at that location. So in my case, it's University of Victoria. And this will automatically start up the package, a Jupyter notebook. And if you haven't installed the software, you just execute the first cell in this Jupyter notebook by clicking on it and hitting Shift-Enter. Now I've already done that, and so I'll start the application as it normally would be started by clicking on the second point. So when we start this application for the first time, you'll see that you have an opportunity to open a model and open some data. So the model can either be local or on the network. Well, if it's the first time you're using it, just download the model and the data over the network. So the first thing is just to refresh regions so that the Dropbox has some data. We could look at Canada data, a Canada model. And we have models for all of the provinces, so let's look at British Columbia and download that. So you can see some information there. You can see more tabs have opened up. Also, download some data, the Canada data that matches those models. We can also do that over the network just by refreshing the drop-down and downloading the Canada data. So now we have data for each province in Canada. So now we can explore the model and compare it to the data. So here's the model that we had downloaded, and we can select to compare that model to BC data and then make a plot that shows both the data and the model predictions for the development of the COVID-19 epidemic in British Columbia. What is shown here is the past 80 days, starting at March 1st. The points are, the green points are the case data. And we also have data here regarding the number of people in hospital, number of people in the ICU, and also the number of deaths in the province. So the left plot is a linear scale, and the right plot is a logarithmic scale of the same data. So you can see that the model is representing the case data quite well. Now what's coming up, of course, is a relaxation of social distancing. Initially in early March, there was a rapid exponential growth in the number of people infected with COVID-19. Social distancing was able to turn around that exponential growth to exponential decline. So that's what's shown here in terms of the model's prediction for the number of contagious individuals. After some exponential growth, there was exponential decline. And likewise, you see the effects on the other other curves as a result of that change in social policy taking place around March 18. So if we want to look a little further ahead, say let's look another 2 months ahead from where we are, so that would take us from day 80, which is where we are right now, the 19th of March, to an extra 2 months. And if we just stayed where we were at this point, you can see that the effect of the virus would be eliminated. However, there is now a relaxation of social distancing, and so this is going to likely increase the transmission rate of the virus. So here is the transmission rate that was seen during this exponential growth period. About a contagious person would infect about 0.42 people per day that they were in the having the ability to infect others. They were not isolated, so almost a half a person per day. Now, after the March 18, the data supports that the transmission rate went down by about a factor of 4. So that led to this exponential decline. So suppose the effects of the change to social distancing was to bring us to a point, not 0.44 or 0.11, but say half of what it was before and twice where we are right now. So we can add a new transmission rate at the current date by considering a new value of alpha, and instead of 0.11, which is currently the value, if we enter 0.22 here, scroll down and turn on this transition, the second transition in the transmission rate, and then finally let's select a time for that to become active, and let's say it's active on day 80. So now we can see the effect of changing the social distancing such that we go up to twice as much social interactions as we have now and about half what we had before. So this occurs on day 80, but it takes a while for any indicators to give us a clear sign that the situation has changed. You can see that the number of contagious starts growing exponentially almost immediately, but we have no direct measure of this. It's only these other points regarding those number of hospitalizations, deaths, and most importantly, case reports that will provide us crucial information. But note that it will take some time for us to get that information after day 80, maybe 3 weeks or so, maybe even longer, before there's definitive data. What's being shown here is a cumulative number of cases. If we look at the the daily number of cases, you can choose that here. So you can see that we've been on this decline. There was a change in testing policy that caused this anomalous reporting numbers to be shown, but we're down here. So we expect these daily cases to start to rise under this scenario. However, with the large reporting noise that we see in these daily reports, it will take some time before one can be certain that we're in fact in such a regime. So we don't know where we're going to wind up in the future transmission rate. If it does happen to be 0.22, it will take a 2 or 3 weeks to be rather sure that we're back into an exponential growth of this size. So that's one thing you can do, and it's an important thing that hopefully this population modeler will be able to help us with, is to try to understand the data that's going to be coming up in the near future, to characterize as soon as possible the new regime that we are in when we start relaxing social distancing. So after you've had some chance to try out this population modeler, you might also want to take a look at the documentation in more detail. You might be interested as well in the example case studies that are shown here. So I've looked at all 9 provinces with significant numbers of COVID. PEI has very few. So you can see that for each province, even though there's been rather complicated situations going on, such as the epidemics in Alberta and also in northern Saskatchewan, that for all provinces, this Python population modeler does a fairly good job of matching the case studies with relatively few parameters. So of course, when there is a new infection outbreak, like in Saskatchewan, we have to add this outburst. We just add it in terms of a date that it occurs and the number of individuals in the outburst. The shapes of these curves are more or less a product of the model itself and not of additional parameters. We can see, for example, that Quebec currently is in a state that this model is suggesting that it's almost in exponential growth now, even before any effects of social distance relaxation takes effect. So I hope you find this informative, and that this tool will be helpful for educating yourself and the public in general about the nature of COVID-19 and in the days ahead as we have relaxation in social distancing rules.